Alright, so let's just restate what it is that we learned here. Case 1 is the obvious case where you have a horizontal line, a constant function. In that case, the derivative is 0 for all values of c on the open interval from a to b. The second case, we assume that there's some value of the function that's above d, which is the y value of the two endpoints. So assuming that it's not a constant function, there's some value that's above, then by the extreme value theorem we know that there has to exist a maximum value on a, b, on the closed interval from a to b. And we're just going to call that maximum value f of c. Let's say it occurs when x is equal to c and the maximum value is f of c. Now, since we've understood or assumed that f of c is greater than d, right? There's some value within that interval that's above the endpoints. Then f of c doesn't occur at the endpoints, and so our f of c is a maximum value on the open interval, and that makes it a relative maximum value. Furthermore, c is going to be a critical number, because a relative maximum always occurs at a critical number. So c has to be a critical number. And since we know that the function is differentiable everywhere on that open interval from a to b, then we know that the function has to be differentiable at f of c, since that's a maximum and hence a critical number and differentiable. Then the derivative at c has to be 0. So this is the proof of Rolle's theorem, which we're going to then use. Now there's a third case, and the third case is just what if f of x is less than d? That means the function goes below the two endpoints, and we would use the same reasoning for this, so I won't go into that. But I'll write it there. Suppose that f of x is less than d for some c on the open interval from a to b. And then we would just use the same reasoning except changing the max to mins, and we would get the same outcome there. So this proves Rolle's theorem, which states that a continuous function on a function that is continuous on a closed interval, differentiable on an open interval, and for which the beginning and the end points have the same y value, that function has to have at least one horizontal tangent on that interval. And I'll clear this stuff out and we'll go on to look at the mean value theorem. Okay, then now we'll continue with the mean value theorem, and what it states is that if f is continuous on the closed interval a, b, and differentiable on the open interval from a to b, then there exists some number c on the open interval from a to b such that the derivative, or the slope of the tangent line to the function at that point, is equal to the slope of the secant line passing through the endpoints. So we say f prime of c is equal to f of b minus f of a over b minus a. And there's a diagram over to the right there. Now the equation of the secant line is going to derive from the point slope form, where our a comma f of a will just be x1 y1, and the slope of that line will be f of b minus f of a over b minus a, and all we're going to do is add the y1 to the other side. So we can begin to replace those values, and that will look something like this. Y is equal to f of b minus f of a over b minus a, that's the m, times x minus a, and that's the x minus x sub 1, plus the f of a, which is the y sub 1. And that's the equation of the secant line. Now what we're going to do next is we're going to introduce this function g of x. And what g of x is the difference between the function f of x and the secant line y. So if you notice, at a f of a, g of x will be 0, and then g of x grows, and it comes back down to 0 again at b f of b. And why we're using this is that this allows us to have a function that satisfies the conditions of Rolle's theorem.